All right, today's lecture is on data collection. And we're going to go through the data collection process. How do you go about collecting data? And really here we're going to mainly focus on practical elements of making web requests. So it's not the most glamorous topic here today, but it's some plumbing that you often need to know to actually do your work with data as a data scientist. So it's good to have at least somewhere a reference on what you want to do. Then we'll talk about common data formats and how you handle them. In particular, we'll talk about three types, about CSV files, JSON files or strings, and XML files. Again, pretty standard stuff, but things that are sort of lie at the foundation of a lot of the later analysis you do, so very important to know. And then we'll talk about regular expressions and parsing. Regular expressions are one of these things that are incredibly useful that you'll probably use all the time. And every time you use them, you'll probably have to re-look up how to use them because the notation is incredibly unintuitive and cumbersome. And so unless you spend a lot of time with them, you won't really remember how you use them. But we will go through it anyway because you use them on the first homework. At least in the 688 section, you'll use them. There might be small uses in the other one, but you'll definitely use them in the 688 portion of the homework. And if I have time, I would like to cover a little bit about the some of the theory behind, not really theory, but allude to some of the theory behind parsing and regular expressions. Because it's actually really a sort of a foundational topic in computer science about how you parse languages and how you know if a certain string matches some expression you've defined. It really gets at the core, honestly, of a lot of computation. And so if we have time, we'll go over that a little bit. Start off with some announcements. So one question I get a lot, which is maybe not the right question for people here, because people here are supposed to be all all off the wait list, but it's for the people that aren't here I'm saying this. They are hopefully watching on video. I've gotten a lot of emails asking if people will get off the 688B section. You will get off that section. We will expand it. I should talk in the camera here. You will get off that section. We're going to expand the course as much as the enrollment to match whatever people need there. It's online, so it doesn't really cost us more space in the room. You will get off the wait list. Stay on that wait list, though, and make sure you have enough units to enroll. So that the reason why people aren't enrolling immediately is because there are people at the top of the wait list that don't have enough units to register, free to register. They're clogging it up for everyone else. So if that's you, get off the wait list or drop the wait list or drop some units. Homework 1 is going to be released tonight. We may, though, not be able to release the autograder tonight. The homework itself comes with test questions, so you'll be able to evaluate all the questions using our own test cases we provide. And the auto-grading is essentially exactly that same thing, just with the cases that we do not provide you. So it should be, cross fingers, and it will never actually work this way, it should be that more or less if you can pass those tests we provide you, you'll also get full credit on the auto-grading. Having said that, things do go wrong, and we actually have requested the software a long time ago now. It's supposedly almost ready, and we're just waiting as well to get our image. It turns out most other courses in Autolab all use the exact same image, but we need additional software, and so we couldn't use that image, and so they're having to create a new one for us, and I don't know why it takes so long, but it does. Should be ready very soon, but the homework will be out tonight. As of this morning, 164 people were enrolled in Piazza. That is less than the even official enrollment, I believe, of the courses, including the B section. If you are not enrolled, enroll today on Piazza. If you are on the wait list or waiting to get in, also enroll on Piazza. You can enroll on Piazza. Nothing will stop you. And you should be enrolled in Autolab. Actually, that should happen automatically. So if you're not enrolled in Autolab, it's probably because you were added very recently. I think we uploaded everyone last night. So if you're not enrolled in Autolab and can't log on, let us know, but you should be. So check again before you let us know. And enroll in Piazza. Do that soon. A few more things. I'm traveling next week. Next week's already a half week because we have a holiday on Monday. I'm not going to be here on Wednesday, though. And therefore, in lieu of the lecture, and it's also a good time to do this, frankly, we're going to have an in-class tutorial on Python. So particularly for people that don't have that much experience with Python, or maybe you're a little rusty, it's been a while, the TAs are going to sit in class and go through some examples in a Jupyter notebook. And so hopefully by then you'll have started the homework, you'll have everything installed. If not, please do install it by the time you start. You can try to follow along in class, or you can watch it online. Attendance on that is optional, though I guess I should add that's probably kind of true for all the classes. You can always just watch them on video if you want, or try to see if you can get by without them, I guess. And it will still be recorded, though. So we will still record it. It'll be kind of a normal lecture, or like a normal lecture, except it'll be the TAs doing a tutorial rather than me standing up here and talking about stuff. There was a great post on the Piazza board. So if you haven't seen this also, check it out. There's a post on the Piazza board which pointed out that if the common patterns of participation on Piazza hold, and my rule is enforced, namely that I'm going to require people to, or that people get full credit if they're within one standard deviation below the mean, then people will get full credit for posting approximately -4 posts on Piazza. You'll get full credit. So, but of course, what I didn't mention, I talked about standard deviations, but I did not mention how I'm going to estimate those standard deviations. So you can do that actually in a lot of ways. It's not just the population standard deviation. It's not the only way to estimate standard deviation. So as I mentioned on the Piazza post, I also reserve the right to estimate standard deviation using whatever estimator I actually want to. So that will, I was very clear. I did not talk about sample standard deviation. I talked about standard deviation in the broad sense. The other thing we might do that would be evil, right? That's one evil thing I can do. The other evil thing I can do is if people start posting questions that are, the answer is a reference to another question because it's already been asked and answered. Not yet, because I haven't said this yet, and I probably won't do this, but I can also count those as negative posts, right? Because people, if they have to get credit for posting, maybe they just start posting questions that have already been answered without reading. So maybe I'll start counting those as negative questions, or at least not counting them as questions. I don't know. This is all going to be a fun experiment and a fun game theoretic experiment. Just participate on Piazza, answer a few questions, real questions, ask a few real questions, etc. Finally, the lunches that I mentioned before that I'm testing out this semester, they're going to start a week from Monday. So I'm not here next week, and then they'll start the following Monday. The sign-up will be posted on Piazza. I have no idea if those are going to be oversubscribed or undersubscribed, by the way. So neither would surprise me. It could be that everyone wants to have lunch. It could be that no one does. I think a free lunch is hard to turn down, so maybe that'll be that popular just for that reason. But we'll see. All right, let's jump in. I've already wasted almost 10 minutes of time. Let's talk about data collection. I have only one projector up. Hopefully everyone can see this a little bit. I bet some people can't see it probably over there, but hopefully people can see it. I typically will write on the board over here simultaneously. Maybe not in this lecture. It's usually when I write math and stuff that it's kind of helpful. Even if I'm writing an equation that's exactly in the slides, it at least slows me down so that you hopefully can all take it in at the right pace because it forces me to write it down. It forces me to go at that pace. That's why I often write stuff down, even if there's no real need for it, even if I'm literally transcribing from the slides. I don't think I'll do that much today because there isn't much math here. There is some code, but it would take a very long time to write code, so I probably won't do that. I'll just try to go at the right pace. If I'm going too fast, please stop me. But of course, you also have these slides you can refer back to later. So as long as you get the big ideas, that's fine. Before I start though, are there any questions about what I just mentioned, announcement-wise or otherwise? Okay, good. Let's get started then. All right, so the first step of data science, this is why we have this course first, is to get some data, not surprisingly, right? You can't do much if you're just talking about generating synthetic data from your own imagination. You probably won't get very far in data science. And typically, though this is kind of these are all kind of ad hoc lists here that you're going to see in this course. They're the things that in my experience, are the most common types of formats, types of ways of getting data you will see, but there are certainly other ones. But typically, when you're talking about getting a data set, right, how do I get a data set? It's one of 4 ways. You just download it, right? There's not much to say about that. Go to some website and download some data. You can also query it from a database. This is also very common. And there, we're going to talk about that lecture after next, a week from Monday, when we talk about relational data. We'll talk a little bit about querying from databases. And And then you will either, the other two forms you're going to get it are usually by querying some API, and these are usually web-based APIs, or you're going to get it from scraping a web page. So there was no intent for you to download this data, but you're doing it anyway through some either violating the terms of service of an agreement or not bothering to pay attention that there are terms of service for a web page. Because almost all of them forbid you from doing that these days. And then we're going to cover these two today about how you do this. And for the most part, like I said, I'm going to cover them from the perspective of just how you, just some sort of code blocks you can use to do this. The details here, I feel like this is kind of just boilerplate that you want to know. It's good to have a reference for. It's good to go through once and see kind of presented in this way. But it's not things that are maybe that deep, how you do these things. OK, so let's talk about querying data from the web. And I should say that for the most part, almost all data you query is going to be over the web. There are a lot of other protocols that existed in the past, FTP. SFTP is still used pretty widely, but that's much more for just downloading kind of one-off files. When you talk about APIs, the vast majority, or scraping web pages, the vast majority of those, the way you'll do that is by issuing HTTP requests. HTTP stands for the Hypertext Transfer Protocol. And I know I've promised in general that we're going to teach you how things work under the hood, but I'm not going to teach you how HTTP works. Take a networking class if you want to learn that. I think you can only go so many layers deep right before it gets started. We're not going to build transistors here either before you start getting a little bit pedantic. And so we're not going to do that. What we are going to do is just use some boilerplate code to issue requests from an HTTP server. In particular, what we're going to use in this class is called the requests library. Who here has ever, actually, out of curiosity, who here has ever used requests before? Oh, fantastic. So like half or a third of the class. And the nice thing about requests is it has a very simple syntax, right? So if I want to issue a GET request, which is the most common HTTP request, you just call request.get. I type in my URL here. And there are a few response codes that are kind of important here. So for example, the status code tells you whether you got anything or not. So if status code is 200, it means everything checked out. You got a web page or you got some content from that. If it's 404, we all know 404 errors, right? When you type in the wrong URL, that's a status code that returned by HTTP. It's saying nothing's there or a bad URL. The content is the actual content you get back. So that is the actual HTML of the web page, or more often than not, it's actually going to be something like a JSON string that you get from querying an API. And the headers also contain some information about how that data is encoded, maybe what type of data it is. In particular, the content type here often describes what type of data. Is it HTML data or is it JSON data, et cetera. OK, so I should say I'm going to kind of go at a rapid pace here because I think this is stuff that either most people know or you can just kind of look at the slides and get it, or look at the documentation and get it. But I still do want to go through it. So if there are any questions, please stop me and just raise your hand and call out. OK, so now let's talk about how you actually go about getting interesting data from a URL or typing some information into that URL. So we've all seen addresses like this, right? We have a bunch of these garbled strings after it, a bunch of ampersands and equal signs, right, in a URL. You've all seen that. And in fact, if you go to Google and hover over a link, if you hover over the link, you'll see the link to the web page. But if you actually copy the link, you'll get something like this. So the link you click on in Google is not actually a link to the web page. It's a link to something that counts how many which web pages you're going to. So Google can actually know what link you're clicking on, and they can optimize their algorithm to give you better search results or make more money usually. But essentially, what these things are from an HTTP standpoint is these are parameters to the URL. And the way you encode these, at least in the context of the request library, is you fill out a Python dictionary that encodes all these things. And this is nice because when you actually type in the URL, if you do it by just putting in the actual string here, you have to do annoying things. Like you have to actually make sure that if you have spaces there, you have to properly encode the spaces in a way that doesn't make it seem like an extra space. If you have slashes, you have to escape all sorts of characters there. You have to do kind of annoying things to make sure this is actually a parsable URL that you can enter, for example, into a web browser. But requests handles all that for you. So especially if you're using a lot of APIs, you'll find that you really are passing a lot of parameters into these URLs, and it would get very cumbersome to try to encode those manually. And so don't do that. Instead, put all your data into a dictionary, a Python dictionary. And I should say, if these things are already looking odd, like what are dictionaries and what are in these import statements, et cetera, you should definitely come to the lecture next time, because I am going to assume that this is all somewhat familiar to everyone, or this level of Python is somewhat familiar to everyone. And then, so I feed in these params into a dictionary here, and then I call params in my function get. I first type the URL, which is just the portion here that happens before the little question mark. And then params I just have to be equal to my parameter dictionary. Right? And then that will query the URL with those parameters as if you sort of did those things. So for example, when you execute a query into Google, the query text is a parameter that you pass to Google, right? Because you're still going to the same URL, but you pass in what your query was. And this is how you do this programmatically, right? So this is going to be something you need to do a lot, essentially. Now I should add that HTTP GET is the most common way to query information over HTTP, but it's not the only way either. So though you don't really do this when you are just reading web pages, if you're querying an API or changing and using an API to change some state in the system, there are actually other HTTP requests as well that are not GET requests. So there are things called put requests or post requests or delete requests that actually these things change some state of the server somehow. So for example, I'll talk about it in a second, but if I'm using an API to access my GitHub account, which you can do, you can actually do things like delete repositories or add, start watching or starring other repositories. Those are things that are changing some state in the server. And so when you do that, you need to actually call other HTTP commands. And normally, whatever documentation you have for an API will instruct you about which one of those calls you need to make. Right? So you don't have to figure it out. The API documentation will tell you what type of call to make. But be aware there are other types of calls too when you do something that actually changes state in the system. All right, any questions so far? So as you go through the world of data collection, one thing you'll do, as I said, is just sort of pull down web pages and parse them in a way we'll talk about next. But the other very common thing you'll do is that you'll encounter are what are called RESTful, or just REST APIs. REST stands for Representational State Transfer. And it really isn't actually, it's not that formal in some sense what it means. There's a whole bunch of definitions about what it qualifies as a REST API. But what it means in practice, at least what I think it means in practice, are two main things. The first of all is that it's using HTTP requests and methods to execute all the transactions. Or I shouldn't use the word transactions because that has a database connotation, but to execute all the commands, you're using HTTP. So I'm going to use GET requests and put requests, et cetera, to actually query the data or change some state in the system. And I'm using the word state now, but that's kind of odd actually, because the other big property of REST APIs is they are stateless. And what I mean by that is that normally when you think about making some set of queries with a server or interacting somehow with the server, you think about kind of establishing a connection. You establish it with the server, and then you send short messages back and forth where it already knows who you are, right? So you sort of say, here I am, here's me. Maybe it'll give you a little, it'll remember who you are from your IP address, and then you just send short messages back and forth with the server to actually execute commands, right? And this is how a lot of internet transactions work, on the lower level at least. But REST APIs are not like that. They are stateless in the sense that the server does not sort of keep a history of your transactions. So every time you issue a new request, you have to sort of tell it all your information again. Okay, and so for example, I'll come to an example in a second of how to do this, but the API I'm going to show in a second, which is the GitHub API, the way I identify myself in GitHub is I send an access token, which is a secret token I know that lets me access my account and do things like create repositories or delete my repositories or do issue pushes, etc. And in a REST API, every time I communicate with a server, I have to send those again, right? So in my URL, I pass my token every time. Now, importantly, I'm passing that token over HTTPS usually, so no one else can snoop and read what my token is. But importantly, there's no sort of way that the server remembers who I am. And I have to re-identify myself and tell the system what I'm going to do every time I want to do it. All right, so just keep that in mind when you're talking about, when you're thinking about using REST APIs, is that you have to be in a situation where you're telling the server who you are every time you interact with it. All right? And in general, so this is sort of my rule of thumb for REST APIs, is if you're re-identifying yourself every time you issue a query, you're probably using a REST API. If you're not, you're probably not, because how else would it, to know who you are, it has to have some other state to the system. So let's take an example of issuing a REST API or a call to a REST API using, again, just requests. Because from a standpoint of the actual transfer protocol, it's exactly the same as just querying a web page. So for example, I can issue a command to get the GitHub API /user. That's just the URL for getting information about the user. And then as the parameters, I pass my access token here, which I'm not going to tell you what it is, because if you knew that, you could then delete all my repositories and do all the things as if you were me on GitHub. So I'm not going to tell you that. But if you want your own, you just go here. Don't tell anyone else is yours either. Just keep it, in a text file that no one ever looks at, right? That's the way we keep everything secure these days. But then once I have that, I can do all sorts of things. So this is one simple command. Basically, this command just gets information. This user command just gets information about me. I mean, it returns, what my login is. I guess you know my login in GitHub now, but that's not too private. What my ID is. I don't have an avatar on GitHub, but if I did, you could get it from that URL, et cetera, right? So the other thing you'll notice is this return string. So the content of the response is what's called a JSON object. So this is an object that was, which we'll talk about in a second, but the way you parse that is different from how you parse normal web pages, which are usually HTML or of varying degrees of correctness in HTML. And I think I'm harping on this point a lot because you have to keep sending this thing. By the way, there's other ways of doing authentication here, which we'll talk about in a second. Right. So if you go to the request web page, in fact, the first example they show is this code here. And this doesn't work. GitHub changed. They no longer allow basic authentication as a way of verifying who you are. You have to use something called OAuth, when a simple way of doing that is via adding this token here. But if you want to build like an application server that actually uses GitHub's API, or sorry, I shouldn't say that. If you want to build a client that lets other people do cool things with their own GitHub account, just having them enter the secret key, create an account and enter the secret key is a little bit cumbersome. And so there are actually other ways of using OAuth for essentially users to authenticate who they are and maintain that authentication while using your application to query the server. We're not going to worry about this, but you are going to use OAuth in the homework, so you will get more familiar with it than you probably want to be. It's kind of confusing sometimes. If you ever go to a website and say, to use our API, sign up for these keys here and enter your client ID and your secret key and other keys too. That's all some form of this type of authentication. It was nice back in the day, but we can't do it anymore. Yeah. OAuth is an authentication system that uses a variety of different keys that identify your user, your session sometimes, and sort of maintain authentication that can kind of be given quickly and revoked quickly. So I'm saying that from a very informal level. And frankly, whenever I have to use it, I just go through the rigor again of saying, OK, these are the things I need to get. Here's what I pass. You can also there actually are also modules for requests that automatically play nicely with OAuth. I'm not doing that here, by the way. I'm just sort of passing them as parameters, which is not always the right way to do it. You can do it that way, though. But it's a way of authenticating that kind of plays nicely with the fact that people want to create their own applications on top of APIs, would be the way I would sort of describe it. And as I said, you'll sort of get familiar with it for the homework. So be more used to OAuth than you really want to be. Yeah. Yeah. So there is still state in the server, right? So there is state in the server itself, because if you put something, you've changed the state, at least of your account on the server, right, on GitHub as a whole. So there definitely is still state there. It's that there's no state in the transactions between you and the server itself. So your requests, it doesn't remember what the last request you made was, essentially. You have to always sort of tell it, I'm still this person, and this is my, and if you want to be more complex, there are also things like temporary session IDs you can get where you can pass that now to the thing. So there are ways around this, but the basic exchange mechanism does not have a state to it. All right, so let's talk about data formats. Again, thrilling stuff here, I know, but things you should probably know. There are three, by my completely unscientific experience here, there are three formats you're going to encounter a lot. These are CSV files, comma-separated value files, which are not separated by commas, incidentally. They're separated by something, but not commas. JSON files and strings, and HTML or XML. JSON stands for JavaScript Object Notation. HTML, hypertext markup language, extensible markup language is XML. So very, very briefly, because you are, at least of those of you in 688 here, there are some, you are going to write a parser for XML, but you'll learn about how to do that in the homework itself. I won't give you the details now, other than a sort of vague outline of how these things work. But the rest, you're going to use libraries to parse. And in fact, by the way, you should always just use a library to parse XML too. It's more an exercise, because if you can parse that, you can probably parse a lot of things, actually. And there are some nasty formats that you may come across. Yeah? Yeah, more transactional type of API. The advantage is sort of simplicity. It's the interaction can be very simple because the server does not have to remember who you are and what you did in the past to know what to do. It also doesn't have to remember, like what page you are viewing right now. All the front end, the display, can be done separately from the back end because it's all just done to these kind of one-off communications. All right, so let's just sort of march on forward here. Comma-separated value files. As I said, they're actually not comma-separated. So the first two words are wrong. I guess there are values, but that's sort of a truism for any data. What CSV actually means is some sort of delimited text file, right, with a fixed, in fact, really has to be a fixed number of columns per row. So here is the first two lines, though I, of course, faked my enrollment here. I'm not enrolled in the class. Or I said I don't think I am. I'm not the first person on the list, at least. Here, when I go onto my S3 page, S3 being our CMU course administration, not the Amazon thing of the same name. This is I can download a course roster in CSV format, and this is what I get. So I get a file where the first line is a header file, so it says what each column in the field or in the document is. And then the next line is actually the content, right? So the content, in this case, it actually is separated by commas, so it's true to its name. But in general, the separator can be, the delimiter can be almost anything, actually. You can often spaces or tabs or vertical bars. It can be almost anything. And one thing you'll notice, there's lots of quotes here. So if you want to have, if your data is comma separated, and you want to have a comma within one of your fields. So say my last, one of my names was something junior, and it has a comma before the junior. How would I do that? Because it would seem like the name therefore would prevent, would parse incorrectly. And so the way you do that is you encapsulate anything in quotes here that is sort of not to be split across multiple fields, right? Yeah. Yeah. So if you have other delimiters, whatever is within your quote character is not considered a delimiter. Yeah. So whatever delimiter is, it cannot. You can have it inside quotes, and it's fine. And specifically, you often, when you parse a CSV file, you should specify what the delimiter is and what the quote character is. The defaults usually are actually a comma and the double quote, but you have to specify what those things are. Now, you do not need those quotes if there's no comma in your field. They're optional. But the registrar here happened to want to be a little bit safe, and so they decided to just encapsulate everything in quotes because they don't, in case we add some, I don't know what we could add. Maybe we add, a comma in some field they never thought would ever have a comma in it. All of a sudden, everyone's scripts run wrong to parse their course lists, and everyone, no one gets into the class, and everyone's upset. So they just go ahead and be safe and encapsulate it all in quotes, even though you don't need to. Now, we're going to talk a little bit more about CSVs and when we talk about relational data, because they kind of, at least, not directly, but oftentimes you will export or load data into a database via CSV files. But for the most part, we're going to use a library called Pandas to parse CSV files. So actually, who here has used or heard of Pandas? Again, fantastic. So this is probably the most common call in Pandas, right? You just read a CSV file. You can do the same with an Excel file. It's a really nice way of storing tabular data. We'll talk about how it's stored and such that later on. But basically, specify the delimiter, specify the quote character, and for our sake, we'll be done. We'll talk a little bit later, if we have time, about how you might go about building one of these parsers. But for now, I'm not going to worry about it. We're just going to say, use this library. It's only at the very end that I'll talk about sort of how these things work internally in some ways. OK, so marching right along, let's talk about JSON files next. So JSON files originated as a way of transferring JavaScript objects around. So they capture a lot of the common data types that are used by JavaScript. But it's sort of come to be a pretty common standard now. A lot of files that have nothing to do with JavaScript now use JSON to pass data back and forth. For example, as one example, you're all going to be using IPython Notebook. I should add that the official name now is called Jupyter Notebook, but it was IPython Notebook for a long time. They changed it because it's not just about Python anymore. Old habits die hard. I'm going to keep calling it IPython Notebook. So to the people of the Jupyter project, I apologize for that. I'll try to be correct there when I can be. But the point I was trying to make is that the Jupyter Notebooks, the .ipynb files, are stored as JSON. So all your data in a notebook, the things you'll download when you start your assignments, that's actually all a big JSON file. And they can include things like images even. So if you have an image there actually will be a portion that just sort of contains the raw data for the image stored as text in a JSON file. So you can get pretty fancy with what you can put in these things. So there, considering how fancy you can get, it's sort of impressive. There are only 5 things that can be in a JSON file. Numbers, and numbers are always considered to be floating point within JSON. There's no differentiation between integers or floating point numbers. Strings, and strings can be enclosed in single or double quotes. Booleans, which are true or false. Lists, which are enclosed in square brackets and have a number of items there. For those that know JavaScript, those are actually arrays in Java, not lists. And dictionaries. Dictionary, again, is the Python name. Just object is the JavaScript name. And these are key value pairs. So you have some key that is a string and some value that can be anything. You actually can have non-strings as keys too, but I think I'm not sure that. I think in JSON you have to have the keys be strings, even though Python can handle keys that are not strings. Certainly. And the big, of course, nice thing about this is you can embed these things hierarchically. So I can have a dictionary. I don't know why I have a list at the end. I have some list that has only one value in it. I guess you could have more things here. But I can have a dictionary whose value is a list. And the second element in that list is itself a list, et cetera, right? So I can embed dictionaries within dictionaries and lists within lists. And this is why it's a powerful file format. Because I can, if I can represent most things with a string if I need to, like an image, then I can also really kind of embed a pretty structured form in one of these things. So when I issue, in fact, my request from the GitHub API, what comes back is actually a JSON string, right? So what comes back is this big string here. I'm not showing you more things. This is kind of boring, though. A lot of different URLs you can go to to find out information about my GitHub account. But this is the when I issued that call that I described before. This is the actual data that comes back. So the GitHub API returns JSON strings as its way of communicating information. And in fact, most REST APIs communicate via JSON strings. It's just sort of they don't have to, but it's become kind of a pretty standard way of communicating data across these types of APIs. So this is the JSON from the GitHub API. And the way you actually import it into Python is you just import this JSON library. It's built in. It's kind of slow. There are faster ones that people have to speed this up if you have really big JSON files. But those sometimes are brittle too, so you can just use this one. And essentially, all you need to do is just call this JSON.loadS function on the JSON string, and that will return a dictionary, because there's this nice mapping between JSON and dictionaries, at least in the outer level, that is a nice Python object which includes all the information you need from your JSON file. And I should take it back. I actually now am uncertain about whether JSON allows non-strings as keys. Does anyone know if JSON allows? Yeah, they do allow. OK, so I'm going to, because I was thinking they might, especially given that Python supports those. So thank you. JSON does allow you to have things that are not just strings as keys. You can't have lists as keys, for example, and you can't do that in Python either. But you can have strings or numbers as keys. I'll trust you now. If that's wrong, I'm going to now blame you. But you can also do things like load it instead of from a string. The S at the end there stands for load from a string. You can also do things like load it from a file or dump it to a string. The dump S will take an object. So just to be clear here, data.loadS takes a JSON string and returns a Python object, which is called data. LoadS does the same thing, but with a file pointer instead of a string. DumpS will take a Python object and return a JSON string. And dump will take an object and a file pointer and write that object to the file. So there's a few different flavors here, but they all do the same thing. They're just transforming between Python and JSON, Python objects and JSON. All right, so marching right along, because I think this is good references to have, but if you need to, you'll probably have to look this up anyway to a certain extent. So let's keep going. So the last format that you'll probably come across is XML or HTML. They are different. The thing that I say is that HTML is like XML but horrible. And the reason why is it does crazy things like, yeah, go on.
Can only use strings as keys in JSON. My mistake was saying in object literal notation in JavaScript you can use non-coding.
Oh, OK. Yeah. So OK. All right. So I am going to blame you now. So redo to my original statement. You can only use strings in JSON as. So I believe what happens then. We should check this now. If you have a Python object with numbers as keys, it will convert those to strings, I believe. And there's another weird thing where actually in JSON there's no need to have keys be unique. So you can have multiple of the same keys there technically in a JSON object. But don't do that. Weird things start to happen in Python then because now you have to have a multi-key dictionary. Just don't do that. Keep your strings unique, your keys unique, and keep them all strings. Just so we don't have we don't have this argument anymore. OK, so HTML and XML. I presume everyone here has probably seen some HTML or done some HTML and XML, therefore, and you're probably pretty familiar with it. There are open and closed tags, right? So you open a tag in angled brackets. A tag starts with the name of the tag, so this tag is called tag. It's maybe a bad thing to call a tag. After a tag, you can have a list of attributes. So attributes are the attribute name and equal to a value. The value has to be in quotes there, either single or double quotes. And you can embed these things hierarchically too, much like in a JSON file, but it's a little less structured here because sort of there can be any content within these tags. So I can have a sub tag now, some content here, and then I have the closing tag. And so that tag closes this open tag here. You can also have open close tags, which don't have any content. They just have attributes. And that's like a tag here, but it's closed with this slash close bracket. And then I'm closing my original tag here. So as I say, the thing I have to say is that HTML is like XML. In fact, one of the things you'll parse, or I'm going to get to in a second, one of the things that you will parse in the 688 homework is the course web page. And when I first did that, it did not parse because it was not valid XML. I had things like open tags with no close tags. Very common in HTML. It was sort of fine for a while. People didn't really think about the nastiness of this from a parsing standpoint. So it's just kind of the standard. And so I had some of these things. XML requires more strict formatting. HTML is a little looser. But more fundamentally, I guess, HTML really is about writing a document in a way that is about display, right? So HTML is about visualizing the data, right? Talks about, italic tags and bold tags, whereas XML is really kind of a data format. That's more the kind of the bigger picture here. It just happens that one instantiation of XML with then a lot of kind of loose elements added would be something like HTML, but they are kind of different too, because admittedly they have different purposes here. One's just to sort of describe data, and the other one really is to display data on a web page. So here, for parsing either XML or HTML, what you will use, at least in the 388 assignment, is the Beautiful Soup library. That's a great name. It's a very nice library too. And what Beautiful Soup does is it's sort of a great library for quickly, I'll say for quickly extracting actual information out of XML and HTML. So if you were just to parse an XML file, in fact, take a look, open up the course web page, and take a look at the source, right? That is the actual HTML code that you will get if you download the page and parse it as normal XML. And there are all these kind of embedded tags within tags, and I'm used to it now because I'm editing it to post things to the website. But if you're not used to it, it'll look like a total mess, and you'll have a hard time knowing what's actually going on there. The course web page is actually an okay one too. If you open up sort of a random web page off the web, that one will really be a mess, right? And so if you have that whole document even parsed correctly as an HTML kind of tree, right? Because you can think of this tag here being the root. It has a child, has two children, in fact. One of them has content, one of them doesn't. If you had to kind of navigate this whole tree to get any information out of the web page, that would be really tedious. And you have to say, okay, how many levels deep am I now before I hit the thing I actually want to get there? When what you really want to do is sort of open a web page, open the source up, look for whatever sort of tags are around that data that you want to get at, and just go right for that data. Right? And what Beautiful Soup lets you do is sort of provide a nice way of doing that via, among other things, this find function. So let's say that we want to, I didn't actually print the return of this, but let's say that we wanted to get all the links off of the course web page. That was interesting to know if this document would be considered one of those or not. It's an interesting recursive thing because I wrote it before this document. Never mind. Let's say that you wanted to get all the links that are included in the schedule section of this course's web page, right? So again, each of those links is many, many layers deep. For those that know HTML, writing a table is a total pain, right? You have to sort of create both a bunch of sections. So we use Bootstrap, which is a sort of a CSS library. And so when you use Bootstrap, you have to have a bunch of sort of div elements that kind of delineate what kind of section there is you're editing right now. So you have a bunch of those. Then you have a bunch of sort of elements defining a table. Then you actually have the actual contents of the table, et cetera. And it's a total pain to actually do anything. Or you need to go many, many, many layers deep before you're actually getting to the data you actually want. But with Beautiful Soup here, what you do is you take the entire web page. The entire web page is stored in this response.content. I should have mentioned actually when we talked about it first, there's also a response.text field, which is the encoding of the web page according to whatever Unicode encoding it uses. But I typically just use content, maybe for bad reasons out of kind of habit. So I called this here to parse that content. I've now created that content in this beautiful soup object called root. And to find interesting information now, I kind of execute a sequence of at least relatively intuitive calls to get that information. So here's sort of what I do. So it turns out, and again, you'll have to do a little bit of digging to find this because you have to know kind of how the website's structured. We have these section tags that delineate the different sections of our web page. So, you know, the schedule, the instructors, the frequently asked questions, et cetera. Those are different section tags. And so I'm going to first try to find the section tag that has the ID equal to schedule. That gives me the schedule section. Then I'm going to find within that, and actually this call here, this first part here, returns another beautiful soup object that is a tree that encapsulates just the sub-elements now of that portion of the web page. So no longer does it have the whole web page, it just has the section portion. And by the way, you'll do the same thing when you write your own XML parser. You'll similarly have to write kind of sub-elements and sub-trees that only contain parts of the full document here. So now this return here has another beautiful soup object that is just that section. And now in that section, I find the table. Right? I find the first instance of a table object, which I happen to know is the course schedule table. Note that that is not an immediate child of this schedule section here. It is many layers deep. And the nice thing about this beautiful soup library is you can actually do that fine. It'll find, and however many subtrees deep it has to go, it'll find the pointer to that table. There's a question over there? Yeah.
So is a section like the HTML tag?
Section here is an HTML tag, yeah.
So like it would identify any HTML tag. So if you had like, so is ID is another HTML tag, right?
So ID here is an attribute. So remember, XML has, or HTML too, has attributes and tags. So what this call is doing is it says, find me some tag called section with an attribute ID equal to schedule. So this one, for example, would match, I first have say find tag, and then attribute, because my name there is attribute, equals value. I pass it just like that, in fact. And that would be how I filtered out those sections. I don't want all the sections. I don't even want the first section. I want the section that has the additional attribute of ID equal to this schedule. Okay. Yeah?
So when we find a table, then it will find all tables, only the first one?
The find command by default will find just the first one. I happen to know there's only one table in that section, so I'm OK to use find. And I also know there's only one T-body section of there. But once I actually, here, I actually do a different call to find all the links, right? So I'm actually going to now say find all A, and A is a tag for a link in HTML, right? So I'm going to find all of these in the document. In this node here, which is a large subset of the document that I've gotten to by going many layers deep. And that's basically how this works. And it's very nice because you can kind of quickly, if you can view the source and you get used to this, you can very quickly find the portion of the code you actually care about. Yeah? Yeah. So what I'm doing is I'm taking now this node in the document, so that is another sort of beautiful soup object that encodes part of the table, and I'm part of the document, and I'm finding the first table tag. So the way you define tables in HTML is with a table tag. T-body is also a tag within a table, and I'm finding these. A is a tag within that denotes a link, and I'm just sort of marching along here, trying to limit my search and then find all the links. And this will give you a set of all the links that you have in my class schedule. Yeah. Yeah. Yep. Yeah, exactly. Find A on the root, for example, would find all the links that happen in the document, regardless of where they are and at what level deep, which is really nice because it's total pain to have to navigate the exact level numbers deep that you want. You never know exactly what that is, especially if the document's not formatted nicely. You'll have to actually count, how many layers deep you are. So it's really nice to be able to do that. Yeah.
After find all, we still have a beautiful soup object.
Actually, find all returns a list.
So
A list of beautiful soup objects.
Okay, so could I do like another find all after find all?
No, because you have to do like a list comprehension or something like that that would then apply, or a map call that would apply some function to every element in that list.
Okay.
It's a list that it returns. Yeah.
Is there a reason like unwrapping would be
Yes. Yeah. You can, and hopefully you'll explore it a little bit on your homework and sort of figure out what's going on. You can also just print it and sort of get a sense of what the hierarchy is from that. Yeah. But yes. All right. So let's move on to the last thing, which is the most fun to teach of all these things, which are, because it's so crazy what you can do with these things, which are regular expressions and parsing. And I really hope I will have a little bit of time. I'm going to try to cover relatively quickly the things I think, again, unscientifically, are good to know about regular expressions, which you're then going to forget and have to look up again when you want to use them in practice. Because I had to look up things to type these lectures even. So I had to remind myself how to do certain things. So don't feel bad if this notation looks crazy to you. It really is crazy. And I don't know if you design it again like this, if you could do it all over again. So let's start with a real, very, very simple regular expression. Suppose I have my document, and I'll just now talk about maybe I have my raw HTML from my that I've queried. Maybe I parsed it with beautiful soup. Maybe I haven't, or I have some other document that I want to parse. Maybe. What regular expressions let you do is they let you they provide a very powerful way of matching certain sequences of text, described very broadly, in your document. So if I have a large document, it's a very complex set of XML, HTML tags. If I just want to find something in that whole document, how do I go about doing that? So for example, suppose I wanted to find the first occurrence of the word data science. And it is cap sensitive here, so this is the first occurrence of the lowercase data and the lowercase science. The way I do that is with this, in Python at least, though I'll quickly move away from Python after a second and talk about regular expressions generally, because they share a lot of similarities across different tools, though some slight differences too. The way you do that in Python is you import the regular expression library called RE, and then you issue a command called re.search for data science, where importantly I'm putting this little r in front of the string. So the little r in front of the string indicates that's a regular expression. And there are some important differences. Most of the time you don't need that, but occasionally you'll find something where the string will parse incorrectly if you don't include that r. So just include the r. Get in the habit of including the r. I don't always do it, but you should in this string. And that returns an object, which is a regular expression match object, which we'll talk about a little bit more. And I should also point out some links. And in the homework, certainly, we'll give links to the documentation for all these libraries, because you're not expected to learn how to use all these things from these, this one example that I've shown you. But it returns a regular expression match object. And for example, I can do things like print match.start, which is the character position of the place where that match was found. So the character position of the first occurrence of data science within, in this case, say within text, which could be, for example, the content of our course webpage. Now there are a few other ways, and now that's kind of boring, right? We can do much more than just that. But before I get to that, there are a few other functions here. So here I'm calling re.search. Just be familiar with a few more. The other things that you may find useful which are all different subtly, are re.match. Match will only match that expression if it occurs at the beginning of the string you provided. Okay, so it will, if it's space data science, that will not match that. Search. So this function here, if text does not start with data science, it will return none. It will not return a match. re.search is what we said before. That one will search forward, try to find the first occurrence of that thing. and return a match. You can also use the find iter, which iterates over all matches there. Or the re.findAll, which returns all matches. Now, one important distinction is that findAll is actually different in that it does not return match objects. It returns a list of just the text that was matched. So I'm not quite sure why they did it that way, but that's the way they do it. So typically, you can use findAll for like quick checks to see how many places it's occur in, but you can't really do many queries on where they occur. Then it doesn't tell you. So you typically want to use one of these other forms to actually do your queries. The other thing you'll do is oftentimes you want to compile your regular expressions. That both makes them a little faster. It does some optimization under the hood that lets you actually do these queries faster, so you don't have to This is getting forward a little bit, but essentially when you issue a regular expression, there's actually some transformations that take place to optimize the ability to search for that regular expression over the file. And this just does that once instead of having to do it every time you issue the command again. The other nice thing about compiling a regular expression to one of these regular expression objects here is that you have similar calls here. You have match, search, et cetera. But you can also specify a start position and an end position for where you're doing your search within. So that's that. If you were to do it in the first place, you have to actually truncate your string to be only the range you want. But here you can give the whole text as input and just specify the position you want to start with. For those that are writing the XML parser for homework 1, do that. Don't try to chop up your string too much. It'll be a lot faster if you do that. All right, so now let's talk about what you can actually do with regular expressions. And this is where they get fun and they get really ugly too. And this is where I might write on the board, but we'll actually see. I may just have ended up having this screen here for no good reason. OK, so the real power comes in the ability for a regular expression not to just match one sequence, but not like data science, but many possible different sequences of characters. And the simplest way you can do that is actually match multiple characters or sets of characters, things like this. So some common ones. For the most part, every character in a regular expression will match that character. So if I have the character A, it'll match an A. The exceptions are these, what is it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 characters, which are special characters in regular expressions. So if you want to match those characters exactly in your text, you have to escape it with a backslash before those characters. And these things are all typically kind of modifiers or wildcard characters or some sort of special character that indicates something you want to match. So the first thing we can talk about is how you match not just one character, so not just a character A, but actually say you want to match the character A or B, right? The way you do that is you enclose those characters you want to match in brackets. So if I wanted to match data science, where data and science could be capitalized or not, I could do something like this. I could do capital D and a lowercase d, data, and then capital S, lowercase s, science, right? And that would match data science with any capitalization on either letter, but no caps after the first one. You can also negate that. So I can match any character except something by including a little caret within the square brackets. I will match any character other than what's in there. There's also some special cases here. So \d is any digit. \w is any alphanumeric character. \s is any white space character, so tabs or spaces or new lines even. And the period is actually match any character, though be careful. The period will not match new lines. So if you want to have matches that span multiple lines, you actually need to pass an extra parameter to all your regular expression calls, which is called read.all. That will make the dot also match new line characters. Yeah? Here? It's the literal underscore. So this is like, function names, stuff like this, right? Actually, function names can't start with a 0 or a 9, but it's common to have underscores, in text. And so for programmers at least, right? And this is written by programmers. So that's why you have this in and out. That's why this counts as alphanumeric. The underscore does. Okay? Where did I mess up here? Oh, yeah. Okay, I messed up there. That should be capital Z. No, it's important. That would be wrong, actually. But just use this instead. Yeah, so you can do things like ranges kind of in the way you would think you'd be able to do them. Those tend to work. But you also can screw yourself up sometimes by doing those, like I just did. All right, so now the next sort of big thing you can do is match multiple instances of the same character or set of characters. And the standard sort of modifiers here is if I just have a single character, that is just match the character A, for example, exactly once, right? If I have a question mark after it, it means match A 0 or 1 times. So if I were to say match this pattern, right, D question mark, eta, that would both find all the occurrences of data and just eta or ada, or however you want to pronounce that, right? If you have a star after it, it means you're going to match that 0 or more times. So you could put as many Ds. It would match this. It would match this. It would match this. And put as many Ds as you want there. It'll match all of those. And when I say, and again, I kind of slip into this saying a lot, but just when I say it matches something, what I mean is that when you run one of these regular expressions on a text document and it includes one of any of those strings, it will return a match at that position. Okay, so that's sort of what I mean when I say match something. You can also match it 1 or more times is a common thing you want, right? Maybe I want to have some. Maybe I want to have something like. I think I actually have this in my next. Well, I even have it here. So if I want to match now any kind of science, data science or otherwise, but I want to at least have some. I don't want to just say nothing science, though since this is doing it literally. If you say like is science, that would also match this, right? So any word before science would match. But I want it to be at least a word, right? I don't want to have like maybe an ampersand, right? Because that wouldn't want to match. But I want to have some word with at least 1 character, and then I want to have a space of at least 1 character. But maybe I have multiple spaces. I still want to match that, and so this string, this regular expression here, would match all instances of something in science, where something is an alphanumeric string, and there's at least 1 space or at least 1 white space character in between them. Right? If I were to, for example, change this to a star here, then there wouldn't need to be a space, right? You could have 1 word where science was the suffix of that word, and that would also match it. Okay? So these are kind of the rules you'll get familiar with as you play around with these things. And in particular on the 688 homework, you'll play around with them a little bit for XML documents, but you'll get familiar with these things as you play with them. Yeah?
The pass after double match the whole string or match the last character?
So this is the entire regular expression, all right? So you will find a match if this whole pattern occurs anywhere. We're not yet talking about, maybe what you're alluding to is something called grouping, which is returning elements of the match. So far, I'm not doing that. I'm not talking about returning anything other than the entire sequence that was matched. All right, so there's no notion of matching part of the string or not. It will match any entire string that has some alphanumeric sequence, some spaces, and the word science. And if that doesn't make sense, I would advise you to play around with it and type them into Python and see what you get out. That's the best way to learn most of these things, by the way. It's a dirty secret here, is that I'm just sort of hopefully able to suggest to you what you should be learning on your own anyway. All right, so moving right along, we have about 15 minutes left, so let me kind of move forward. The next very important thing, which you'll probably want to use, is something called grouping. So oftentimes, you don't just want to know if I match some string or not. I actually want to extract certain portions of that string. For example, one thing you will do on the XML parser assignment is you will write a regular expression that can match XML tags. Okay? And if you do that, you probably want to be able to extract what that tag was and maybe what the attributes were through this process, right? And so what you can do with regular expressions is put parentheses around any portion, and then if you find a match, there's this groups call that actually will return what portion of the text matched within that group. All right? So if I run this query here, so this is saying there's some term, this is, some term here plus one space in this case. So some alphanumeric term plus one space plus science, where science can be capitalized or not. I've surrounded this word that precedes science in brackets, and I've surrounded the word science in brackets. And I'm doing that one because I don't know if it's capitalized or not, so I want to get back information about whether it's capitalized or not. But when I match this, I get a match object, and then I can print this match.groups, or use this match.groups function to actually see what terms corresponded to these different groupings in the regular expression that I just matched. Yeah?
Basically, you're checking like if the substring of the string you gave, if like a substring also matches.
Well, yeah. So it's the whole string had to match. For anything to return from this call, the entire regular expression has to return a match. If it doesn't match the entire thing, it will return none. But within that, there are sub-portions that match each different element here, right? So this first thing here was matched to the word data. This second thing here was matched to the word science. And so these calls return those sub-portions. But it will still return none. There can be some word, right, that would match by itself, but without the word science after it, it will not find a match. It will not return anything. Yeah? You can, yes. And there's some nasty rules there, and I'm not going to require you do it for the homework. But yes, you can. Everything in the homework you don't have to, but definitely you can nest. Especially these. You can nest all sorts of things, actually, in regular expressions. But here you can definitely nest, yeah. And then there's some, I think it's like the roots come first in the ordering before the children, I believe, in this groups call. I think that's the way. It could be the other way around. It's one of those two. Either or. All right. I think we're almost getting to the end here, so that's good. One other very useful thing, just going beyond just matching text that you can use regular expressions for, is the ability to actually change your file. So this is going to happen a little bit less in data science because you usually want to change the data that much. But maybe you do. Maybe you want to convert to a different format, something like this. You want to clean up data. Actually, oftentimes when you clean data, you do have to substitute other values. So, what if I want to find all instances of data science and replace it with schmata science? This is how you would do it. So you use the re.sub call. There's a similar one for compiled regular expressions. So you could similarly make a substitution call on a compiled regular expression. But this is sort of the simple one. And of course, this is sort of an easy case, right? Where you're taking this thing here exactly, and I'm replacing it exactly with this. And the way this can get powerful, though, is when you have expressions that are more complex than just simple matches, right? So use all the groupings, all the wildcards, everything like that we've talked about before. When you do the substitution, you can actually refer back to the groups that you had in your original expression. So for example, if I want to take the string, actually, does anyone know what this will do? What this one will do, out of curiosity? Can anyone guess what this would do? Yeah.
Just replace data science with data schmata.
Yes. Right. So what this does is that this regular expression here matches data science, right? And it matches it whether it's capitalized or not, and it stores in a group both the word that preceded data science and the first letter. So I could kind of remember whether it's capitalized or not, essentially, right? So if it's capitalized, this grouping here would be a uppercase S. Otherwise, it would be a lowercase s, right? And I replaces them with this thing. And what I'm doing here, what this \1 means in the context of a regular expression substitution, though you can actually also use them just in a single regular expression, is it refers back to the first group that was matched there. So whatever that word was, put it there. And whatever this thing was here, put it there. So I'll sort of keep the capitalization of my second word. But I'll replace the science portion with schmience. And that sort of changes the text where I keep the full first word, keep the capitalization of the second word, but replace the second word around a little bit. And this is where they start getting really powerful, these things, especially if you do something which is sacrilege, which I'll talk about why in a second that is sacrilege. But you can also use these back references, they're called, within a single expression. So for example, I can match some string, and then see if that string occurs again later in the expression. And for those computer scientists in the room, you may already know why this is sacrilege, but if not, I'll explain it in a second. But you can get sort of very, very fancy here. OK, I think this is the last. Yeah, this is the last thing I'll say before I just talk about a pointer, which you're actually getting to use because none of this stuff is complete enough to learn to do anything. Yeah. No, you can do that. Yeah. I'm just not grouping them here. I just didn't put a group around the white space. But you absolutely can do that. Yeah. Maybe I'll move on because I have about 5 minutes left or 7 minutes left, and I want to finish these things. So I'll quickly move on. We can chat after class if you have questions, though. OK, so the last two things I'll say is there is an order of operations in regular expressions. So one thing I haven't mentioned yet, but which is also defined, is this bar notation for or match this expression or this expression. But if I have something like this, if I have something like ABC or DEF, that means the strings ABC or DEF, not ABC, AB, C or D, and then EF, right? So the or operator has very low precedence against just items in sequence. You can get around this using parentheses, so I can match sequences like A, then followed by BC or DE, and then an F by properly enclosing those things in parentheses. And now if you kind of are bothered by this, because this also creates a group, maybe annoyingly, you can get around that by creating parentheses that do not create groups with this little notation here. I don't know why they picked that. They probably should have picked a different notation entirely for parentheses and groupings, but this is the way they do things. And finally, the last thing I'll say is, and this actually I think gets to the heart at what some of these things are doing internally, is that regular expressions will match greedily, meaning they will match the biggest expression they possibly can, which is often not what you want. So if I want to have an expression like this, which says, find an open bracket and a closed angle bracket, and everything in between, return that, and you apply it to this text, it will happily return A all the way to this end A here, right? Because that is an expression that is contained between two brackets. And it will match the biggest thing it can. That's the default behavior of a regular expression. If you don't want that, if you want to match the smallest thing it can, you put this question mark after the star. And that can precede anything. So that can precede, plus question mark. It can precede anything like that. Question mark actually also works. It'll match 0 if it can, or 1 if it can, or 1 if it has to, rather. But if you use this, you will get just the A term. Okay? And so that's sort of a tricky thing that hopefully, though, will codify a little bit about how these things are working internally and why you might want to use certain expressions over others. Because your first version of a regular expression will almost always fail at doing what you actually want it to do. maybe it will match it, but it will match much more than you want it to match too, right? So it would match just this, but it will match much more also. And finally, I should add there are many more things you can do with with regular expressions. There are many extensions that have been added that I'm not even going to get into here, but which, as a whole, make these things very, very powerful. I believe, actually, for instance, you could solve the entire XML. I haven't quite confirmed this, but believe you could actually solve the entire XML parsing using one enormous extension-based regular expression. So if you want to do that, by all means, more power to you. I have no idea how we'll even grade that, because that, it's one of these things that, I mean, I guess it's auto-graded, so if it works, it works. But if you can do that, fantastic. I'd love to see that, but I don't recommend it for anyone that is trying to accomplish the assignment in an understandable way. Look at the docs and try things out. The last thing, I have 2 more slides here. I'm only going to cover the first slide of these 2 because, and you can sort of think about the last one that I'll cover as well. But the last thing I'll say about this is that these are very useful tools, but they're actually also fundamental questions in terms of computation and theoretical computer science. And so what I mean by that is the following. When you learn about sort of automata theory and the theory of computation, you'll learn about things like finite automata and Turing machines and these kind of things. And it turns out that regular expressions and other types of languages, that, like XML and these other kind of things, fall into a hierarchy of types of expressive languages that a computer can recognize. And when I say recognize, what that means is if I input a string to some program, the program has to say whether or not that string belongs to the class of languages it's meant to encode. So if I feed in a string to regular expression, that should say whether or not that string actually matches that regular expression, right? It turns out that regular expressions belong to kind of a very limited class of algorithms or languages called regular languages. That's not quite true, actually, because there have been a lot of additions, like backtracking or back references, rather, that actually no longer make it belong to this class. But kind of basic regular expressions belong to the class called regular languages, which can be recognized, can be flagged or not, by what are called deterministic finite automata. A deterministic finite automaton. When you start moving up this hierarchy, you actually get different classes of languages that can be represented by different types of constructs of computing, up to the most powerful one called recursively enumerable languages, which can be recognized by any Turing machine. So for those that don't know, and again, this is sort of more for the CS people in the audience, but Turing machines have this model of computation that has an infinitely long tape where you can add, or you can make symbols in the tape and read symbols in the tape. You can write and read from that tape. But it's infinitely long, importantly. And it turns out you can actually, any language you can represent with a Turing machine are what are called recursively enumerable languages. And then by marching down this hierarchy, you get different things here. So for example, a context-free language can be represented by a non-deterministic pushdown automaton. This is a finite state automaton that also has a stack associated with it. So again, this is not going to be tested on. We're not going to test you this. But if you do know some of these things, it's worth looking them up a little bit, because it'll give you a good sense of what you can and cannot parse using finite automata. So I'll put this last slide up just as we can filter out. But there are a bunch of languages, for example, that could not be parsed by any kind of basic regular expression, and similar ones that cannot be parsed with any as a context-free language. So you couldn't parse it even if you had a stack augmented with your finite automaton. So I don't have time to ask the questions here, but think about these questions as you go on. Can you parse a CSV file with a regular expression? What about an XML file with a real regular expression, right? Not a cheating one, or an XML file. Think about these, and hopefully it'll help you on your homework. I will see you all in 2 weeks, because I will not be here next week, but we'll have a Python tutorial next time.